Hi, my name is Fotinis Mistira-Liviki, and today we're going to speak about deep neural networks. But let's start first with a bit of history. Back in 1959, Hubel and Wiesel did a very exciting experiment with a cat. They positioned the cat in front of a projector where they project a straight line in different angles, and they have put a microelectrode in the visual cortex of the cat. And what they discover is that the neurons are responded best to a specific angle. In particular, when the projected line was completely vertical, the neurons were fired the most. Let's see about the human vision. Our eyes are very sensitive in the contrast, edge of light, and less to the overall illumination. And you can also see a demo where the change in the background illumination, the visual system continues to be responsive to the contrast between the circle and the background. Let's see now in this slide the analogy of the human vision and the convolutional neural network vision. So the human vision first tries to detect edges and lines, and then combine them to shapes, and then to objects, and finally to reconstruct the face. Likewise, the convolutional neural network in the first layer tries to detect edges and lines, and then combine them to shapes, and then to objects, and finally to a face. And here we can see the intuition of the discrete convolution. We have the convolution kernel. In this example, it's an image of an eye. And we try to detect where is located this eye in the image of the face. To do that, we move the small image of the eye in all possible directions in the image, and whenever we found an eye, we put 100 as an output, and whenever we don't find an eye, we put a 0 as an output. And this is the discrete convolution. Let's see now a typical convolutional neural network structure. Usually, as an input, we get an image, and then we have a layer of a convolution layer, a max pooling layer, and this we can make as many layers as we want, convolution and max pooling. And at the end, we have to have a flattening layer and a fully connected layer, and this goes to the output. Let's see now a bit of a history of the convolutional neural network, how all this started. This started, as we said, in 1959 with the experiment of the cat. And a few years later, Fukushima created the first CNN architecture, and he called it neocognitron. In 1989, Jan LeCun creates a backdrop-style learning algorithm to the Fukushima CNN architecture. And many years later, in 2010, the first large-scale visual recognition competition called ImageNet took place. And the first error rate that was reported, it was 26%. But only 2 years later, in 2012, AlexNet won the ImageNet recognition with 16.4% error rate. Today, this error rate is as low as 3%. And why it took so much time for the CNNs to get better in accuracy? Because of the computational power and because of the lack of large label data. Now in this slide, we can see the long short-term memory neural network and the recurrent neural network. The recurrent neural network is a typical neural network where we have the features, the input layer, the hidden layer, the output layer, and the output. But we also have a recurrent connection between the hidden layers in order to keep information of previous timestamps in the network. Here the context information is used, however, it's impossible to store precise information over a long period of time. And this causes the vanishing gradient problem, and usually R and N forget information after a short period of time. And that's why we introduced the LSTM neural network that adds a memory cell with 3 gates: the input, the output, and the forget gate. Thank you very much.